We are now going to discuss crystallographic operators in the context of a group, a point group. So we have been talking about a lot of things in combination with translation vectors and making lattices part of, making lattices that are consistent with particular rotations. But now we want to do a step back and say what kind of point groups, that is, things that we're headed towards hanging on each lattice point in order to build more complex structures. So like we were saying, there could be a group of motifs around the lattice point, and they themselves have symmetry. And then we want to do later is when we get these point groups, because they only operate around a point, we haven't put them into any translation yet. We would like to then drop them in later and derive all of the 2D space groups. Now, how do we get these things? Well, you can imagine if it's focused around a point, then here's a point. Then, well, what can I do if I'm not using translation? Well, I can combine things like a rotation and a mirror plane, for example. And we're going to do this first by inspection, and then we're going to derive another combination theorem. But you can imagine as we add our rotations and mirror planes, we'll get sort of certain point groups. That is, these things all have particular symmetries, around, etc., around the particular thing. And remember, it's just operating around this point. We haven't dropped them in to a lattice yet, right? So this thing will be called a point group. And we want to develop these symmetries because, of course, in crystals we can have, as you'll find out later, something called a basis, which is a certain number of atoms that are sitting around a lattice site, and they're reproduced, through the crystal structure, and that's kind of how you can think about the geometric equivalent that we're doing here. So we're going to start off by creating what's called the 2mm point group, and we'll talk a little bit about the notation in a second. But we'll derive this by inspection, more or less. So we're going to create the 2mm point group, which doesn't exist yet. We haven't talked about it yet. We've talked about 2, which is a twofold axis, but we haven't talked about 2mm. And we've talked about m, which is a mirror plane, but we haven't talked about 2 together. So our first example, again, no translation operator, and we're going to add these 2. So let's just do it by inspection. So let's imagine that I have, indeed, the twofold operation here, rotation. And I'm going to add a mirror plane that we're going to call sigma 1. Okay? Now let's draw a motif around this. So if I draw this guy here, he's going to be reflected across this mirror plane, right? Over here. Right. Also, this guy is going to have to be, or both of them actually, are going to be rotated 180 degrees around, right? And so if I look at this one come around 180 degrees, right, it's going to end up being here, right? And the same thing for this guy, 180 degrees. Of course, I can't draw. Now notice that already we know from our previous work that the twofold axis is compatible with mirror plane. You can see it here, because what I started with was just saying, okay, fine, I take one object that reflected it, and then both these things are rotated. But you can see down here, these 2 are related to each other by sigma 1. So everything's consistent, everything's compatible. However, if you look at this, this pattern a little more closely, you'll notice something. You'll notice that actually this guy, this guy, this guy, this guy reflected about a mirror line, or mirror plane as we've been calling it. And so there's actually a mirror plane that's induced when I put these 2 things together that we'll call sigma 2. So when you combine a twofold axis and a mirror plane, you get another mirror plane. When you combine a twofold axis with this mirror plane, you get another mirror plane which is perpendicular to it automatically. So this is what I was talking about before, is an induced symmetry, because we didn't create it. We only added, this twofold axis to this mirror plane. And automatically, you could see when we just do the operations of sigma 1 and 180 degrees rotation, you end up with this extra lattice plane sigma 2. So that's kind of interesting, right? Because it suggests then that we have another combination theorem coming later, where if we have something like a pi, right, and you operate on it with sigma 1, somehow we're going to end up with a sigma 2, right? Now this is a very specific one, and the question is, can we generalize it? And later we will generalize it. So this would be called a point group, and in our definition, 2 is a twofold axis, so that's present, and we added a mirror plane. But the reason we have to add another mirror plane, actually I should probably do this the other way around with color, because we did it first with the red twofold axis, and I added one mirror plane, which is sigma 1, and then I ended up with a completely new symmetry element that wasn't there from the beginning. It's not induced by the operation of one on each other. Remember, this twofold axis is not a fourfold axis. This thing isn't rotated 90 degrees. It's rotated 180 degrees, right? So, but just by operating and having these four pieces of the motif being consistent with red, it automatically induces a sigma 2. And so we have to have an extra m to represent that, and that's why it's called 2mm. So now if we go back to our point groups, definition of a group, right? So this is a point group, but it's still a group. And we're going to have the following elements. We have 1, which is our identity element. Remember, that was definition of a group. We have to have that. We had our original mirror plane. We have our twofold axis, right? And point A is in the middle here by definition. And then we induce this other part sigma 2. And so this shows you that's a group, because if I have these two in this one, I automatically get this one, and so we suspect that we might have then a group. And so let's look at our official proving of that with an identity matrix. So this looks kind of complicated, but it's really just a simple way, if you're into group theory, to show how this works. And I think you can see now how with that sigma 2, which was induced by the presence of a pi and a1, we now suspect that every two elements here should induce the third. Because remember, that was another part of being a group, and these two should induce this one, right? So the way we're going to prove that is we're going to take the elements of the group, and we're going to put the elements of the group along the y-axis as well. And of course, what this does is represent essentially what I was just talking about, looking for each member to affect the other one and produce another member of the group. And the way you see that, that's why you form this matrix. Because, for example, when I choose here sigma 1, right, I am going to operate on it with 1, and I end up with sigma 1. So this is just saying that when I take this element, sigma 1, and I operated on it with this element, I end up with that, right? Now let's look at sigma 1. If we were to look at our motif and start off with some object here, and I were to say, let's take, remember, we're trying to say what this equals, but we're taking this one, sigma 1, operating it on with sigma 1, and we get 1. Now how do we see that? Well, remember, this is our what we were calling sigma 1. So if I take my part of my motif, I operate on that object here, right? That is the product of just having sigma 1. Now if I take, after that operation sigma 1, I operate on it again, so I have sigma 1, sigma 1. It actually just reflects it back, and I'm back to where I was, which means it's a 1, right? If you do nothing, it's just a 1. That's the identity element, right? So if I take sigma 1, I reflect it again, I end up with 1, right? Let's continue to go down this column. So if I were to take sigma 1 and I do this operation again, let's just show that there. So sometimes we can write this as, here's the first one, and then there's the second one from the operation of sigma 1 itself. And now I want to do a sigma 2. Remember, this was sigma 2, right? So now we'll take this one and we'll reflect it across here. So this is number 3, right? Now, what you want to do to find out what the operation is then is, I did sigma 1 and then I did sigma 2. Let's see how the 1 is related to 3, and that will tell me what the operation is. And of course, when I look at 1 and 3, I see I have a 180 degree rotation between these two, so it creates an A pi, and that's what we have here, right? And then for the final example, you could say, let's switch pen colors before it gets too confusing. You could say, all right, I'm going to do sigma 1 again, 1 to 2. But this time I'm doing A pi. So I'm going to rotate 180 degrees. So this time, this is my number 3. And now I say, how are 1 and 3 related? And it's clear they're reflected about sigma 2. You can see that here. Right? So again, just to repeat that, the first operation is listed here. Right? I do this one, and I then do a pi rotation. So first thing is sigma 1. Then I rotate around, give me the red 3 here. And then you ask, what's the relation between 1 and 3? And it says sigma 2. Right? And so on. You can practice yourself for the rest of this matrix. But at the end of the day, we finish this matrix, and of course it tells us we have a group. And the way that you see that is, well, we put in an identity element in each one. So that means, for example, sigma 1, when I operate with 1, I just get sigma 1 because, well, nothing happens, right? It's just itself. So that's pretty obvious. The other thing is that in every row and column I have a 1, which means that I always get an identity element in each one, and it means an inverse exists as well. So, for example, sigma 1 and sigma 1 give me a 1. Sigma 2 and sigma 2 give me a 1. That's because in each one of these elements here, it doesn't have to be this way, by the way, with different, in a general case, but it turns out that each one of these undoes itself, right? Now, it doesn't have to be there. It could be another element undoes it, and but in this case, because this, what I was showing you before, if I reflect here and I reflect back, nothing's changed, right? And so obviously for mirror planes, if I do this one and I do another one, I'm going to get a 1, because it's as if nothing happened if I operate twice with the same one, and that's why I have this diagonal here. And it turns out that's the same with A pi. If I do a rotation, I do another rotation, I'm back in the same spot, so it's a 1, right? So because these inverse elements exist, that is that I operate, I do an operation, and there's another operation that I do that then always gives me a 1, right, as if nothing has changed. And then finally, all the elements, anytime I operate on any diagonals, meaning that, like, for example, sigma 1, sigma 2, or sigma 2 pi, A pi, or A pi, sigma 1, if you look across the rows and columns, I always induce another element that's already in the group. right? So those are our three definitions. Remember the identity element, the inverse, and the combination of the two elements produce a third, which in this case, we're talking about operations. So that's kind of how you can use an identity matrix to prove that we have these elements of group. Now, what I've done here is through inspection, but what I want to do later is to develop the general case for this, because remember, this is a specific case of having a twofold axis with a mirror plane inducing another mirror plane. But you would think that there are common things about mirror planes and rotations, and we'd like to make that general case, because then we go through the point groups and we derive them relatively quickly. We can just know by inspection, if I have a rotation like this and I have this plane, I'm going to get a plane over there, right? So we want to develop the most general one so that we can use it as we're developing. So by inspection, we've already derived our first point group. That's not, it's a new thing, right? I mean, remember we had developed all of the rotations that ahead of time we're thinking, right? Because we put them in the lattice. We saw that these are rotations that are compatible with translational symmetry. And so we're not going to do any ones outside it, like fivefold axis, because they aren't compatible. You could have a point group, by the way, with 5, because it's not in a lattice, right? But we're not going to play around with that, because what we care about are the ones that are the symmetry elements, which can be put into a lattice. And we have our lattices. It's just that now if I combine M with these rotations, I can get new groups that are in there. So 2mm is another one. And so besides just dropping a twofold axis or a mirror plane into one of these lattices, I can now drop this motif here, which is a 2mm motif. I can drop that on every lattice point and see what other symmetries it induces, assuming that it's compatible with the particular translation vectors. So we'll stop there, and that's our first one by inspection. And what we'll do is soon we'll go into developing the general case of that. So then as we go and develop, we don't have to do each one by inspection. We can actually do the opposite. We say, well, when I combine these two elements, I know I'm going to get a mirror plane over here or something like that. All right, so we'll stop there.